So, what I'd like to do today is to talk about this evidence that we found in Mexico that supports the drawdown theory, which was first presented by Josh Rosenfeld in about 2003. But more importantly, to show you the evidence from this outcrop and how it's putting this theory to the forefront, and how we're finding all this evidence that supports the theory and the events that happened at that time. So there's the co-authors there are Don Van Nieuwenhuis, Joe Davis, Josh Rosenfeld, and James Pindell. First of all, I'd like to show you the location of the field area, and then just mention one slide about what is the Gulf of Mexico isolation theory, for those of you who don't know about it. And then we'll talk about the paleogeography at the time in this basin, which is the Tampico-Misantla Basin in eastern Mexico. I'll talk about the Paleocanyons, which we've mapped in that basin. This key bitumen bed, which is the key piece of evidence in the basin for what happened at this time. And then some conclusions at the end. So the field area itself is onshore eastern Mexico, right in here, just to the south of the city of Tampico and to the north of the city of Poza Rica, and to the west of the Tuxpan platform. Here's the Mexico-US border here and the present-day coastline. I'll stand in front here, it's a little easier. So the Gulf of Mexico isolation and drawdown theory was first proposed by Josh Rosenfeld and James Pindell in 2003. It's a time when they proposed that the Gulf of Mexico was isolated from the world's oceans by some kind of barrier which was created by the Cuban arc docking against the Florida-Bahamas platform. So when the Gulf of Mexico was isolated, we would have had evaporation of the waters within the Gulf of Mexico at that time. Probably not complete evaporation, and that's something we don't understand at this point, whether it's complete or partial. But it would have happened at the rates of about possibly 1 meter per year, with sea level falling about 1 meter per year. And Josh, in his paper, suggested that sea level could have gone down just within the Gulf of Mexico basin up to 2,000 meters below sea level. We may not get salt deposits. We've found one well in the Veracruz Basin which has cored some salt that correlates to this time. We haven't had permission to view it yet, but we wouldn't expect to see evaporation unless we had 90% evaporation of the water within the Gulf at this time. And then at the end of this isolation period, we would have had a breakthrough, a rapid catastrophic breakthrough, which then refilled the Gulf of Mexico within a matter of days, really. Very, very short period of time, rather like the Messinian in the Mediterranean, which is an analogue to this event, a much more recent analogue. There's a lot of evidence for this around the Gulf of Mexico, and the evidence is mounting, and Josh has a totally separate talk which he can give about that if necessary, but he's written many papers about the other evidence around the Gulf of Mexico. Some big questions still remain. When did this happen? How long did it last? How many times did it happen? How far did sea level drop? And is this somehow linked to the PETM, the Paleocene-Eocene thermal maximum, which coincidentally occurred at exactly the same time? Is that focused enough for people? That it looks a bit blurry from here. That's work. Is that good? Okay. And one thing it does require is a little bit of out-of-the-box stratigraphic thinking, because we're not dealing with a normal regression, transgression sequence at this time. So what the paleogeography was thought to be at this time was like this, with the Gulf of Mexico as an isolated sea a land barrier across here, isolating it, and this was totally separate from the world's oceans. So we were dealing with an evaporative history in here at this time. And you can see the Tampico-Misantla Basin is very well placed to record what happened in the basin at this time. So the stratigraphy, what we will be talking about is the Chinontepec Formation in Mexico, which ranges in age from 38 million years to the KT boundary, which is on this scale 65.5 million years. I think it's moved to 66 now. But basically the KT boundary, so a large sequence represented by the Chinontepec Formation. And the Wilcox fits in right here. So this, it's not very easy to see this, but the Wilcox fits in here. And what we're talking about, this sequence boundary A here, this is what I'm going to concentrate on, about 54, 55 million years, which correlates to the upper-lower Wilcox boundary, as we know it in the Wilcox stratigraphy here. So about that time here, this is what we're going to concentrate on right in here. So the paleogeography in eastern Mexico at this time can be represented by this diagram. Here's the Faja de Oro reef trend, which is the Tuxpan platform basically. The red dots represent the cities, so PR is Poza Rica right here. Tampico would be further north up here. The H is Huejutla, which you've probably never even heard of. The little C is the town of Chinontepec, which the formation is named after. And you'll see these on the next map I show, just to reference that. The red line here represents the future Eocene basin. In the Eocene, the basin was much, much smaller than the Paleocene basin. So what we had in the Paleocene was an entry point up in the north. We had a deep water basin. This is the Tampico-Misantla Basin. Turbidites deposited to the southeast. Some of those show reflected paleocurrents back to the northwest, and we have slumping off the uplifted Sierra Madre Oriental into the basin towards the northeast. So it's basically a deep water basin with lobes and channels within it. A lot of carbonate sands in this basin. So we're going to go forward to the Eocene and look at this area here, a slightly smaller area. This is the same red line as on the previous slide. And in the Eocene, what we see are these canyons which are cut into the Paleocene sediments. And this is shown by field work here. This was shown by over 1,300 samples that were taken in the field. And you can map these canyons from the ages of those samples. And then at the mouths of these canyons were these small submarine fan deposits. So we still had a deep water environment, but somehow between the Paleocene and the Eocene, we had these canyons cut into the Paleocene to create the fairways for these Eocene isolated submarine fans. I'm going to show you a cross-section through the basin here, BB prime, which was the result of a 2012 study. So we gave these canyons sort of informal names here. The Acatapec Canyon is the one I'm going to concentrate on today. But I'll show you this cross-section. This is the cross-section BB prime from northwest to southeast. And it's actually a chronostratigraphic diagram. It's a Wheeler diagram. So what we're looking at is time here. The red and the grey areas are missing time in the wells, which are the vertical columns here. So there's a lot of missing time in the sections. And the common missing time are the sequence boundaries here. And here's the sequence boundary 54, which spans a much wider time interval than the other sequence boundaries that we mapped up in here. So it's about 1 million years of missing time in all the wells in the basin at this time. And this cross-section shows that clearly in the chronostratigraphic sense. So if we go back to the canyons, here's the Acatapec Canyon up in here. We're going to concentrate on looking at the evidence in that canyon today. So here's a zoom. This is a zoom of that canyon. There's several pieces of evidence in here for the canyon existence. We've got an incursion of the Cretaceous tertiary boundary here on the outcrop map of the geologic map of Mexico. We've got evidence of samples within the canyon itself. We've got a road cut here, which I'll show you. We've got another section here, another measured section by Pemex, and then finally we'll talk about the bitumen outcrop right in here. But first of all, I'll show you this section which shows the erosion into the Paleocene sediments. And it's a very classic outcrop showing this huge erosional surface into the Paleocene thin and medium bedded turbidites on the left here, with an Eocene canyon fill dendrite in the canyon itself, and a huge erosional surface between the two. If we move along the canyon, this Acatapec section here, a measured section, which has been studied by Gustavo Diaz in 2008 and other people. So here's a sketch of where that measured section is up in here near the village of Acatepec. It's a very nice road cut, 75 meters thick. We did outcrop gamma ray through the whole section. And what this section shows is a typical canyon fill sequence with a sequence boundary at the base here. Sequence boundary 54 is right in here. We see pebbly mudstones at the base and some slumping as well, grading up into sandstones and sandstones with shale clasts, and then at the very top, more thin-bedded channel levee deposits. So a typical channel canyon fill sequence about actually 75 meters plus thick at this point. We did take some samples from here, samples 1, 2, 3, 4, and 5. Unfortunately, the guy who took the samples couldn't get them in the right order here. But these samples are basically devoid of in situ fauna. But they all show reworked Cretaceous nanofossils and forams, except number 4, which was completely bound. So we can't get a lot out of these samples in here, but there's an awful lot of reworking of the Cretaceous in this section right here, which we see in other places. The other thing I forgot to mention, the Paleocanyons here are to the east. So when we're in this section here, the Paleocanyons are in an easterly direction here, conforming to the orientation of the canyon. So let's move on to the bitumen bed itself. This is a Pemex measured section that was measured in 1978 when they did field work on horseback, and they show the Paleocene Eocene contact right in this measured section here. So the bitumen bed is exposed in this canyon area. Prior to March 2015, in the literature and all the geologists that had visited it, they thought it was a coal. It's a black bed with sandstones above and below it. Everyone was describing it as a coal. The bed, as we see it now, what we've excavated in this bed is 13 to 28 centimeters thick, but in 1984 there was a geologist that went there, described it as 60 centimeters thick, so less than a meter thick usually. It contains many shale clasts. These clay clasts have baked rims on them, and I'll show you some pictures of these, and very delicate edges to them, so they've been transported very short distances and incorporated into this bitumen bed. Some other characteristics of the bitumen bed are it's barren of forams, nanos, and pollen as well. There is no fauna that we found within this bed yet. It's low sulfur, it's not biodegraded, it has conchoidal fracture, it fluoresces under UV light. There are no stratifications, no mackerels, non-continuous fractures or slits typical of bitumens. When we sent this sample off, we first sent it off to a coal expert, and he said it's not a coal. So these are the results from the geochemistry. Oil and gas is released immediately on exposure to UV light. The hydrocarbon index is 600. The conclusion is that the bed is a fossil bitumen. Sometimes people call it a pyrobitumen. That's another name for it. And the key here is the evidence that this bitumen was deposited in a subaerial environment. So the key evidence here is that this was a fossilized oil seep flowing downhill along an erosional unconformity, and it has a very smooth upper surface to it, so the oil flowed very easily. It wasn't solidifying easily, and it flowed down onto a fairly flat surface, and you'll see that when I show the pictures. The bitumen itself and the overlying sediments immediately overlying are barren of microfauna, underlying and overlying sediments. It's immediately overlain and underlain by bathyal sediments with no shell marine facies in it. Within 10 or 12 centimeters of the bitumen, we see bathyal microfauna in the sediments. And the key evidence really is that are the limonite tubes or root casts which are preserved in the sediments between 0 and 1.7 meters below the bitumen bed. That's the key evidence. So this is what the outcrop looks like, and you can see it's kind of a overgrown, scrappy looking outcrop with a black bed in it right here. This is all that was exposed in someone's yard. Not a very impressive outcrop. But this was a picture that we discovered. Mark Bidder actually took this in 1984. A bit more impressive when there was less vegetation there, and you can see the black bitumen bed in here, and you can see some odd things going on, like that looks like a sandstone along strike from the bitumen bed, and there's black material down here under this scarp. Why would it be here and not here? And then you can also see the brown clasts within the bitumen itself. Maybe the light's not so good in here. But there was certain things we saw in this photograph which alerted us to some very strange things going on. This is a measured section that Mark Bidder did in 1984. Here's the bitumen bed, 60 centimeters thick. Very thin sandstones above and below it. The only thing you can notice is sort of a lack of sand right on top of the bitumen bed here. But this is the best measured section we have since it was done in the 80s when it was a lot cleaner. So when we took samples in March of 2015, we took samples above and below the bitumen bed here. And this is a plot of the nanofossil abundance, the foraminifera abundance, and the limonite tubes stratigraphically above and stratigraphically below the bitumen bed right in here. You can see the limonite tubes are only present, they're very abundant at this point right here, but only present below the bitumen bed. There are none above the bitumen bed. And the foram abundance varies a little bit, but the nanofossil abundance really increases below the bitumen bed here. These are the ages that were determined by Don van Nieuwenhuis from graphic correlation of these samples. So we know that the bitumen bed was deposited within the hiatus between 55.8 and 54.95 million years. And I'll show you some evidence for that in a minute. The pollen, there is no pollen present in any of these samples, which is a very unusual observation as well. Sometimes it's what we don't find that's more important than what we do find in this particular outcrop. And 100% reworked Cretaceous nanofossils right on top of the bitumen bed itself. These are some of the limonite tubes that we found here. They're about 1 to 2 millimeters long. You can see them in the sample here, little pieces down here, but quite abundant in these samples below the bitumen bed. This is the graphic correlation, the work done by Don van Nieuwenhuis, taking the tops and bases of the species and plotting them on a time scale here. He can answer questions on that if you'd like to afterwards. But this is the line of correlation above and below the bitumen bed. So we have a hyadal surface in here, or a terrace as it's sometimes called, of 850,000 years, between 55.8 and 54.95 million years. And this is where we see above this point we see abundant reworking of Cretaceous fauna above the hiatus, and very little, if any, reworking of Cretaceous below this hiatus. Also, we see that in the Zircon data. These detrital zircons were taken from sandstones below and above the bitumen bed. This is from 165 centimeters above the bitumen layer. This is 90 centimeters below the bitumen layer. And we see a very high percentage of Cretaceous zircons above the bitumen. This is the Cretaceous right in here, with this peak of zircons right here, but very low abundance of Cretaceous zircons below the bitumen. So here's the outcrop. It's in a neighborhood in Chinontepec. These black blobs here, the houses here. Here's the outcrop represented by this orange bar. Last year we drilled a couple of core wells to determine the lateral extent of the bitumen bed. This number 1 well hit the bitumen bed, the number 2 well did not, so we know that it pinches out or disappears before that, 16 meters between them. So this is the strike of the bed here, represented by the blue bar. This is the owner of the property right in here. And when I was in the field there, I wanted to follow this bed. Let's follow it along strike here and look in this area to see if we can find another exposure of this bitumen bed. But couldn't find anything in here. Couldn't find anything at all. The neighbor, whose name is Ray, lives here, and he said, oh, when they built this house here, we saw this black bed about 1 meter wide in the foundation of this house here. I thought, Ray, you're crazy. It's not even on strike with the bed that we know here. And I just dismissed it at the time. But when we went back in September and we excavated a pit right in here. We excavated this pit, shown in red right here. We saw that the bitumen bed takes a 40-degree turn in the pit and heads off right underneath that house right there. So Ray was right. But we found that this bitumen bed is actually along an erosion line conformity. And we see the erosion in this pit here. So this is about 50 odd meters. So we assume that we've still got 50 meters of not exposure, but presence of this bed under here. We plan to go back and excavate more of this in May of this year. So this was the coring and trenching operation last year. The drilling rig came from Mexico City, and we were trenching along strike here to expose the bed. We wanted to clean it up. We hired Ray and his cousin to dig out here. This is Mark Bitter right here. So we're digging out along strike, and we start to follow the bitumen bed, and it splits. We wonder what was going on there, but this split is just a large clast that we see in the bitumen bed. So we expose more of it down in here. Here's a white bed, which is probably some kind of ash bed or something. We're still studying that bed. So we're digging out along strike. Here's that large clast. There's more clast within it here. The white bed underneath the bitumen bed. There's a whole crew working there, digging this out. And then it takes a turn. It takes a 40-degree turn towards that house that I pointed out. And it's about 28 centimeters thick at this point right in here. So the whole thing, as we excavated, thickens in this direction and then takes a 40-degree turn along the unconformity. Then we filled it all back in, covered it in plastic, and so this was the end result of the excavation here. This was the group that was there last September. And this is a sketch of what we found. So on this sketch, here's the 40-degree turn, here's the clasts in here, and then where we took the samples, shown by the red circles here. The blue ones show a bathyal in-place fauna. The red samples are barren of in-place fauna, but these ones above here show reworked Cretaceous in here. So there is some bathyal sediments in the clasts here. So these clasts have come from up the section here and then been incorporated into this fossilized oil seep here, which we believe came out of the side of a canyon, down the side of a canyon, and then to a flat terrace of some kind, and was preserved and pinches out less than 16 meters away from this point in the outcrop, with probably about 50 to 100 meters of relief, at least 50 meters along this cliff face here being preserved. So something like a modern analog might be in Carpinteria, California, where we see a cliff, we see oil seeps coming out of the cliff, and we see a sort of a fan-shaped feature of bitumen at the base of the cliff. The difference is that this has a very irregular top to it. The one in Mexico has a very flat top to it, apart from the little undulations from the clay clasts that are within it. So this is what we see in California. We see a very irregular top because the oil is very viscous when it comes out here. If you go here in the winter time, the oil doesn't get further than about this point. In the summertime, it flows further down this fan feature. So as far as out-of-the-box thinking is concerned, this is the laundry day on the Chinontepec here. The Chinontepec oil seep has a very flat top, implying that oil flowed freely on a relatively flat surface, unlike the California examples. And if this coincides with the PETM, which it seems to do, we know that temperature was a lot higher at that time, and any oil seep would have flowed very freely in this type of subaerial environment. The red class, which I mentioned, indicate baking. Were there forest fires occurring at this time? What was happening with the climate? Something was causing these baked clay clasts. And when we look at how much section is missing at the outcrop, we know the rock accumulation rate was about 12 centimeters per 1,000 years above and below this feature. So if we've got 850,000 years missing, we've got about 100 meters possibly of erosion into the sequence to create this particular canyon. So, let me go back here. What I want to do is show you just a little PowerPoint movie of what maybe the formation of this canyon looked like. We have an age date here, and this would be the Paleocene section here, and the blue representing water, of course. So we'll go through what might have happened at this time. Sea level falling about 1 meter per year, exposing the sea floor, the Paleocene, methane being released at that time, maybe contributing to the PETM, a canyon forming, vegetation, canyon deepening, further deepening about 100 meters deep, and then the oil seep coming out of the side of the canyon being preserved on one of these terraces on the side of the canyon. Then we don't know how much time lapsed before the catastrophic infill of the Gulf of Mexico. But at some point afterwards, we had the catastrophic infill of the Gulf, and then the deposition of the Eocene sequence on top of that. So these kind of sequence of events to create what we see at that outcrop today. So here are some of the clasts. This is that large clast within the bitumen, which is bent 90 degrees here. Very delicate edges on it right in here. So it hasn't come very far, and it was pliable at the time because it's bent 90 degrees. The other class we see, we do see some limonite tubes in some of the clasts as well. So that's evidence that these were exposed and then incorporated into the bitumen bed. So they appear to have been entrained within the oil seep. They didn't fall down the cliff, land on top of it. They were somehow entrained in the flow as it came down this cliff. And the red class, the real mystery here. Not all the clasts show red rims, and the red class are from within the Paleocene. We did take some Paleocene nanos from one of these larger red clasts as well. Here's a picture of some of these red clasts. This is a piece of a larger clast here. You can see the very intense red rim to it and an orange interior. So the original clast was this big. I dug it out and it broke up as we dug it out. This sandstone here has a very red exterior to it, but it's grey inside. This was broken open by us with a hammer to see what was inside, because we were convinced it was some kind of a Triassic sandstone, because it was so red on the outside, and you can see the bitumen on it too, but it was completely red on all sides, and we broke it open, it's grey in the middle. And then we see these other red clasts within the bitumen here, some of which I've shown with the arrows here. So those are a bit of a mystery. But we do know that to get a brick, when we create bricks in an oven, we have to heat them to 1,000 degrees centigrade in a kiln. And forest fires can get up to 800 degrees centigrade. So there is a possibility that maybe these were created by forest fires at the time when it was subaerially exposed. There's some explanation for these clasts. How far did sea level drop? Well, this seismic line is offshore eastern Mexico here, published in 2012. I think Barbara was one of the co-authors on this. There's a large erosional feature here, which when you put this erosional feature on a map, that line would be here, that erosional feature would be 100 plus kilometers wide at this point. It does coincide with the extension of the Chinontepec Canyon here, which cuts down into the Jurassic. It is a sort of projected into that line, and so we know that possibly sea level went down to this point and beyond into the Gulf of Mexico. So much further than this point, sea level dropped in the Gulf. So, in conclusion, what we see are these Chinontepec canyons, several of them within the basin, which did not exist before about 55.8 million years. The canyons are evident from the incursions of the Cretaceous Paleocene boundary and the proximity of the Eocene to the Cretaceous. Sometimes it's less than a kilometre from an Eocene outcrop to the Cretaceous outcrop in these canyons. An outcrop containing a preserved bitumen bed was deposited in a subaerial environment at the Paleocene-Eocene boundary, which is the same as the upper-lower Wilcox boundary. This indicates an extremely rapid sea level fall of greater than 200 metres at about 55.8 million years, lasting about 850,000 years, with no apparent shelf facies preserved in the sequence. The authors believe this is a record of the isolation, drawdown and catastrophic refill of the Gulf of Mexico in the early Eocene, late Paleocene. This is coincident with the PETM, and the release of methane from the hydrates in the Gulf may have been the trigger for the PETM event. Chronostratigraphic analysis, the Wheeler diagram I showed, shows a second Gulf of Mexico isolation may have occurred at about 45.7 million years, and lasted about 500,000 years. We've not worked on this, but we want to throw that possibility out there. The exploration implications are that basin burial history needs to be modified slightly. Exposed carbonates would have had porosity enhanced in them, any exposed carbonates at this time. Canyon fills may contain preserved fluvial sediments, and large volumes of Paleocene and older sediments were reworked into the deep Gulf of Mexico between 55.8 and 54.95 million years. And along that, with that idea, this paper came out in 2007, Art Berman and Josh Rosenfeld, and before we knew these dates, they actually picked pretty close to where they thought this hiatus would be and where the sediments would have been transported much further into the Gulf of Mexico at this time. And I've asked Art where this came from, but no clue as yet where this actual came from. But it's in a publication anyway. So just wanted to thank a few people. Juan Ampercoon of Tampico, who takes us and helps us and makes sure we don't get into any trouble in the field. Mark Bidder for first showing me the outcrops in 2004, and the Mejia family for access to the outcrop. Thanks also to Lynn Goodoff for geophysical support back in the late 2000s and first alerting me to the presence of the unconformities in the basin. And additional thanks to Jeff Stein, Paul Cornick, Judith Potter, Mark Fowler, Hamid Senai, Brian Horsfield and Henry Yang, Tim Lawton, who is part-time in Querétaro University, and Alejo Beltran in Zurich, who did the Zircon work as well. Thank you very much. There has been, yeah, and it's interesting because when we sent it to GFZ in Germany, who did that work, they said it indicates it's coming from a tertiary source, which doesn't leave much time. We're at 55.8, we've got 10 million years basically. But they then admitted it could be an Upper Cretaceous source. But it's either Upper Cretaceous or Paleocene source. That it appears to be, yes. Yeah. Josh could probably answer the questions better on that. He's more familiar with the other evidence around the Gulf. But it appears to be. Let me show you quickly on this map here. I didn't talk much about this particular canyon, but what people call the Chinontepec Canyon is actually this exit canyon right here. And that's where we see, and I've looked at the 3D and Lynn has mapped it, Lynn Goodoff has mapped it. You see 650 meters of erosion into consolidated Cretaceous and Jurassic sediments. It cuts all the way through the Cretaceous into the Jurassic right here. So you've got to explain how can you get that type of erosion in consolidated lithified sediments.
As I said, I'm not
in a
saying
short
you
period of
shouldn't
time.
have the drawdown. It would have a canyon that would be much bigger than ordinary. But
Right.
older than that, there are other canyon cuts we see.
There could be some from the Chicxulub event.
Well, that's what I'm thinking.
You've got a huge catastrophic event then, which would have had some kind of huge backwash involved with it that could have cut.
And that
who knows
would be
what kind of
microfracture.
That's a very good point, Larry. And the key here is it's two-dimensional, not one-dimensional, but what we see is this classed here, we see a little bit of topography on here, and we see this sandstone pinching out onto that. So we know these sandstones came after this event, and this was not injected along an unconformity. That's the convincing part to me about this outcrop, that it was not oil injected into some kind of unconformity. It's not a fault, because we see this white bed, which very conveniently is very photogenic and correlates across here, so there's no cut through.
Gross similarity.
Yeah, and I see your point. A lot of people have brought that up. Yeah, even Jim Pindell said, well, this could be injected along a fault plane. Well, you know, this white bed proves it's not a fault, but then we've got this pinching out of this sandstone and this topography here.
And the evidence of subaerial exposure is pretty important too.
Yes, it is, yeah. Yeah, we have to go from bathyal to subaerial to bathyal rapidly. Right? Yeah, that's the whole key to this outcrop. Right in here. We're still, as we excavate this way, we're going to excavate further along here. I'm sure we're going to have more surprises this year too. Scott?
Steve, have you had an opportunity to date or identify the clasts in more detail? You had mentioned that they were very pliable.
Yeah.
Was curious about the age and if you can draw any inference from
These are, the only age we have from these ones is Pliocene. Paleocene. Coming from
Happy there.
Pliocene would be a miracle, but no, the Paleocene coming from up the cliff somewhere. Now, I'm waiting on the Zircon date that we've actually got in place zircons in this bed here, and Alejo Beltran in Zurich is dating those zircons, and we should have a good age date on this bed right here, which would be interesting to see how it ties to the graphic correlation age dates. But what we really need is you know, a good bentonite bed or something above the bitumen.
Do they form there during the
No, they
Cretaceous, or were they
transported from the Sierra Madre Oriental to the west.
More evidence of rework.
More evidence of reworking. But there's one sample was from below the bitumen, one above, and the one below showed virtually no Cretaceous zircons in it, and the one above showed really abundant Cretaceous zircons. So there's a huge change in depositional style, I guess you'd call it, between here and here.
Oh, different sediment source.
Source terrain.
Sediment source terrain too, yeah.
Well, if there are no more questions, I want to join you, or I want you to join me in thanking Stephen
Thank you very much.
for